Good day. So we'll continue our lecture on automata theory today. And today we'll be looking at context-free grammars and pushdown automata. Now, let's start. I'd first like to go into something called when can we say the solution is effective, or when can we say the solution to the problem is efficient? Now, when we say the solution is effective, it means that the solution solves the problem completely, so that it solves it without giving room for inadequacies. That's when you say a solution is effective. But when we say a solution is efficient, we say a solution is efficient if it solves the problem with limited amount of resources. Now, if a solution is effective, does not mean it's efficient. And a solution is efficient does not mean it is effective. But the goal of the design, no matter any design, effective solutions comes first. Solving a problem always comes first, even if you are writing the program. Solving the problem is after you solve the problem that you can then say, okay, at what point, how can I refine? How can I make what I'm doing? How can I make what I've done better? So, this note the difference between the two. Now, where do all of this come into our work? We'll see. Now, let's do a little bit of review for grammar. Let's consider two languages. One, A, B raised to power n, greater than or equal to 0. That means that lambda is part of this language. You should know that by now. And the other one is A raised to power n, B raised to power n. The question is, these two languages, are they the same? Let's try and see. Let me try out from my notepad, and let's try and put in something. Now, here's my notepad. Let's do the first one. A, B raised to power n. So for A, B raised to power n, we can have strings like A, B. No, okay. Since it said lambda is part of it, so that's not the first string. Because it said n equals to 0, that's not the first string. So the first thing is supposed to be lambda. Well, let me use E for lambda for now. So we can have A, B, A, B, A, B. Have A, B, A, B, A, B. Like that, A, B, A, B, A, B, A, B. But for the second string, we can also have lambda. Like I said, I'm using E for lambda because I don't want to start looking for the lambda symbol. So for E, for second one, I mean, we're gonna have A. Now notes. That's why I said, are these two strings, are they the same? At the end of the day, mathematically, you may want to say that for both L1 and L2, you can say L1 will give you equal. If you have 4 A's, you're gonna have obviously 4 B's also. And for L2, quite the same. The number of A's will be equal to the number of B's. But the way computers process them is what we're trying to look at now. Because in mathematics, you can just say you want to bring in this n inside and then say, okay, they are the same. We'll see if they are the same, like I'm saying. But for the second language, we have to first do. Now, wait for it. So let's say n equals to 4. N equals to 4. Yes. Then you have to do what? A. Then say B. There's a reason why I'm going through it. I'm going through it. It's for you to be able to see something. Let's say you want to say AA, then BB. Now here, if you watch it, this is a pattern. You just want to see A and B are together. You just need a certain number of A's and B's. Just pick A's and B's, they are together. Just give me 4. Just so what do you basically need there? All you need is just need a counter just to be able to count A's and the A's and the B. But for the second example, you need more than a counter. First of all, you actually need a counter. But beyond the counter, you need a register. Why do you need a register in the second language? You need a register because you're not just counting A and B. You first counted number of A's. You first counted A's. Now, of course, your counter is going to do that for you using a counter. Now, don't forget you don't have two counters. It's still the same counter you're going to use. But it's not even a question of number of counters. After you count, you want to store the number of A's. You want to store the number of A's that you got. So, using what? Yes, a register. Now, after you've gotten the number of A's using that register, you can then say that, okay, when you're now counting B's, when you are counting the B's, what are you doing? At what point will you stop? If you have let's say you have the first A. After you counted, let me do another one. Let's say let's do n is equal to 3. So you count at this point. You don't even register anyway. For initially, I mean, so you counted A. Now you want to count B. Is this okay? No. Why? How do you know it's not okay? Because this is not equal to the number of A's. Where are that one? Is it equal to the number of A's? No. Where are that one? Is it equal to the number of A's? Yes. We can then now stop. So this second language requires a counter and a register to solve. Not like the first one that are together. Now, let's see. A friend of mine once asked me this question when we're designing. That was like 3 years ago. Funny enough, I didn't get to answer him because the answer didn't jump at me. I just told him I'll think about it. I knew the answer, but the answer wasn't just coming to me at that point. But the answer is so simple. The answer is what we're going to answer in today's class. Now, let's try and design an FA that will solve this problem. Let's design an FA that will solve this problem. Now, let me pick finance automation. So, I want to solve. Don't forget what I want to solve is right over here. I want to solve these two using a finance automation. So, to solve it in finance automation, let me pick these two. Now, for the first one, I can just easily do A goes to Q1, can then do B goes back to A. No. B goes to Q. Then I can make this excuse me. I can make this. I can make this the initial state. I can make this the final state. They will solve the very first one. No questions asked. If you are in doubt, let's try and run it. Multiple one. You see that this will only pass A, B. Let's even start with A. Let's also do A, B. A. No. That's it. Let's do A, B. So that's how we read it. A, B. Now, let's run this. Oh, why is it rejecting? Oh, seriously, I know it's rejecting. It's going through the wrong direction. It's supposed to be okay. So actually, don't mind me. This is not supposed to be final state. This is supposed to be also the final state. So this will pass. This will pass. One. Yeah. So that's one again. Good. Good. So you can see with a finite transformation, we say this solution is effective. Like I defined effective and efficient solution to you the other time. We say this solution is effective. Yes, it solves the problem. As a matter of fact, it won't solve any other thing. It solve this problem with accurately. It will even pass AA or pass BB. If it does not see an A and a B together, it will never pass it. This is an effective solution for A. Now let's try for language one. Let's try and solve using finite automation again. Let's try and solve the second problem. Let's implement the second language using the finite automation. Let's see what we get. Okay, so to solve that other language, that is A raised to power n b raised to power n. So you want a certain number of b's, then a certain number of b's. So the best you can do with that is this. Let me remove this final state first. Now, depending on how I decide to do it here, I think I'll just want to remove this and this. So the best thing I'll do here is to look over this first. Call this A. Then look over this, call it B. Then link these two. Should I use an A or a B? Actually, it doesn't work. Let's just say B. So, and I'll call this the final state. So I'll call this my final state. Now, don't forget the definition of effective and efficient solution that I gave to you just now. Now let's load our input. So let's do multiple one again. So we want to do A. We want first to A. Oh, okay. But by the way, it's supposed to be L n raised to n greater than equals to 0. Well, just understand, I don't want to pass lambda. I'm not interested in passing lambda. Let's just take it to 1. I'm not interested in passing lambda. It's not what I want you guys to see. So I don't need it. So let's do A, B. Okay. Let's do A, A. Let's do A, A. A, A, B, B. A, A, A. A, A, A. A, A, A. B, B, B. Then let's do A, A. Let's do A, 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 B, 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 B. So yes, let me this one. Good. Do you think now a question? Do you think this solution is effective or efficient? Now let's see this. Let me put in A, B, B. Let me put in B, 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 B. Let me put in A, A, B, 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 B. Do you think they will run? Yes, of course they will run. Let's see. Accepted. So now, will you say this solution is an effective solution for the second language, A, B, N? I mean, you want it to first count A's. You want it to have number of A's, then have number of B's. Do you think this, or count the actual number of it? Do you think this is an effective solution? No, it is not an effective solution, because it does not solve this problem completely. If somebody was to put A, B, B, A, B, or this other strings, our machine will pass it. Therefore, this is not an effective solution. We'll continue in the next slide. I mean the next video.